Okay, folks, so real quick note on notation. I'm going to continue to use the small dot to mean multiplication, while I'll use a larger, bolder dot to mean the dot product. I'm not really concerned about that. I know that sometimes if I'm writing it may be difficult to tell which is which, but you should always be clear simply from context. If I've got two vectors, then the operation between them needs to be a well-defined vector operation, and so I can't use the times sign, so it must mean a dot product. And likewise, it makes no sense if I've got two scalars to talk about the dot product between them if I'm considering them as scalars. So it should always be clear from context, but I will use a bolder dot to signify the dot product and continue to use the small dot to mean multiplication. So I want you to go ahead and pause the video, and I want you to work through number 2 on your own based upon the work that we did in the pre-work. You should be able to get through these. And if not, I'll cover them in a moment, but pause the video and try these, and we'll resume in a moment. So folks, I went ahead and worked through these. You can see I did the dot product operation. I chose to color code the coordinates just to remind you of how you can visualize the dot product operation, where you multiply like components of the two vectors and then sum them up. We got an answer of 8. For the cross product, remember that you set up this array, and frankly what we're doing is we're writing a matrix, and we're going to take the determinant of that matrix. But we don't really need to learn matrix theory for this class. Right now you can think of this as just an array where we line up I, j, k, and then notice that the order matters here. Since my first vector used is v, since the first vector being used is v, that first row needs to be for vector v, and the second vector being used in the cross product is u, and so that that third row there, or the last row, needs to be for vector u. That does matter. The order does matter there. And then remember what we do is essentially, and I'll just draw one of these, for the I hat vector, one way to think about it is for the I hat vector, you block out the current row and the current column that I hat is in, and then you notice that we end up with a smaller array here, and that's what you write that you're going to take the 2 by 2 determinant of. Let me clear those out. And so to do the 2 by 2 determinant, remember you take the multiple of that diagonal, -3 times 5, and then subtract from it. That subtraction has nothing to do with the sign of the values. That subtraction is in the formula for the 2 by 2 determinant, minus the product of 2 and 0, I hat. Also, something to be very careful of is remember that the I hat and k hat components are simply the values of their minor 2 by 2 determinants, but for the j hat we need to have a minus sign there. Okay. I didn't do the last one. I want to talk about the last one. Here I'm asking you to compute u cross v. So the first thing I'm going to do is I'm going to set it up as if we were going to compute it. And just to reiterate the issue of order. So here is, we write out the I, j, and k hat in the first row, and in the second row I'm going to fill not with the components of v but with the components of u, which would be -1, 0, 5, and the components of v, which are still 2, -3, 2, and we compute the determinant of this expression just like we did in part B. And I'm not going to do that, but I want to emphasize that because we've got different rows, this is going to give me a different determinant. However, and you can check this for yourself if you compute u cross v directly, it turns out that u cross v and v cross u are what we call anti-commutative, meaning that the answer to this should be negative the vector v cross u, which we computed in part B, and so I can simply take my answer from before and multiply each of the components of v cross u by -1, and I will have the cross product of u and v. So let's go ahead and do that. That would just be 15 I hat plus 12, 15 I hat plus 12 j hat minus 7 k hat. Folks, if there's any questions on that, let me know. So the next thing I want to do is I just want to keep pushing you guys with this multivariate function notation. And so I want to emphasize one way of thinking about the dot product. And I encourage you to keep trying to use this function notation where I'm going to define the dot product, d, as a function that takes two objects. It takes an object from Rn, which we could think of as a vector, and another object from Rn, again another vector, so two vectors in Rn, and maps them where? Very important here, notice that this is R1, this is the real numbers here that we're mapping these two vectors to. So the dot product takes two vectors and outputs a scalar. And how do you do that? Well, you simply multiply like component. If you've got a position vector, you simply multiply the like components together and then sum them up. Okay? So the picture looks something like this, and I'll just do it for the 2D case. Maybe we're in R2 here, and say we have two vectors. Maybe we've got this vector here living in R2 and this vector here living in R2. Then what the dot product's going to do is it's going to map these two vectors onto the real number line. So it's going to take these two vectors that are in R2, it's going to take them as inputs, and it's going to output some number. You know, if here's 0 on the number line, it's going to output some number here where that number is simply the dot product of these two vectors. Let's say we call this one u and we call this one v. Then this would just be, if we did the dot product, let's go ahead and write, I need a pen here. If we did the dot product of u and v, it's going to output then the number that we get when we take u dotted with v. Okay? And I'm drawing this picture here because I think it's really helpful to see that the dot product takes actors from Rn, whatever dimension we are in for our vectors, it takes vectors and pairs them with a number on the real number line. Yep, I think that's all I want to say about that. Okay. Same thing here. We can think of the cross product. Now, notice here in the dot product, I said, hey, this works for any n. For the cross product, we are only defining a cross product in R3. You can define things that behave like cross products, sort of, in other dimensions, but usually you don't end up with all of the properties that we like our cross product to have. So I had some students ask a great question, what if we did the determinant of a 4x4 matrix? Why wouldn't that work? And you would come up with a vector that's orthogonal to the other vectors, but it wouldn't behave as well as their cross product does in 3 dimensions. So we really only compute a cross product of 3 dimensions in this class. And so this only works for R3. Be careful with that. Okay. And so suppose we have these two component functions. Well, what does this do? So the cross product function takes two vectors in R3 and maps them to a third vector in R3 based on this computation right here that we just looked at an example of. So the picture that looks like that is that we may take, and here I'm going to, usually when we represent the cross product, we represent everything sitting in the same XYZ plane. Here we got x, y, and z, and let me pick. Here's one vector. Maybe we'll call this vector u, and then we'll take another vector. We'll call it vector v, and maybe it's sitting right here. And we take these two vectors, and I guess since I gave them in component functions, I probably ought to orient them on the, put them on the. Since I've given them as components, they really need to be as position vectors. So let me draw, let's say here we have, say, u, and here we have, say, v. And the cross product of the two of these gives me a new vector in R3, x, y, z. So I take the two, I do the cross product operation, and let's do the cross product of u and v. That's a u there, that looks a little sloppy. That's the cross product of u and v. And careful here, we got to see which way is it going to be pointing. By the right hand rule, we take u and v, and so our resultant vector, I need a different color, let's do orange. The resulting vector should be coming out maybe something like this, where this vector right here is the new vector we get when we took u cross v. Okay. So again, usually when you look at a diagram in a book, what they will do is they'll put all of this in just one x, y, z plane, and there's nothing wrong with that. But I want to emphasize that the cross product is a sort of operation that takes two vectors in R3 specifically, and outputs another vector in R3. So yeah, in a book, and I think that this is a very good way to represent the cross product. Here we'd have Here we'd have v, and here we'd have u, and then we would just simply represent the cross product as that vector that's orthogonal to both of those and heading in a direction that obeys the right-hand rule. And careful, what's the magnitude of that vector? Remember that the magnitude of that vector is obtained by finding the area of the parallelogram formed by those two. So that's going to form some sort of area there. And that area, so let me just write that area there is equal to the magnitude of u cross v. Okay? So this diagram can get a little cluttered, and sometimes it's hard to remember how we think of this. The cross product operation takes two vectors in R3, maps them to another vector in R3, whereas the dot product in Rn takes two vectors in Rn and maps them to a real number. And I do want you to be thinking about these operations this way. It will help you keep track of what type of objects you're dealing with later on in the course. So we'll go ahead and I think I want to stop the video there, because then you guys go ahead and work the breakout room questions.